In this video, I'd like to continue our discussion of graphing rational functions. And in the previous couple videos, we looked at the graph of y equals 1 over x and y equals 1 over x squared, essentially the parent functions for these rational functions. And from these two graphs, we can make some generalizations by noticing some patterns. Now, to really understand each of these functions, you need to make a table and plot points. But it is a bit of a time consuming process because you have to plot a lot of fractions to be able to understand what happens around the x value of 0. Since notice, as x gets closer and closer to 0 from the right side, the y value starts to approach infinity. So imagine putting in tinier and tinier fractions like a tenth or a hundredth or a millionth, and the y value will get larger and larger. For instance, if you plug in 1 millionth, then you can ask 1 divided by a millionth, or how many millionths can fit into 1? The answer would be 1 million. So the smaller the fraction, the larger the y value. And likewise, on the left-hand side, when you approach 0 from the left, the y values start to approach negative infinity. And it's very similar to the logic we used when approaching 0 from the right side. When you approach it from the left-hand side, the only difference is that you're plugging in negative numbers. So instead of dividing by, let's say, a millionth, you would divide by negative 1 millionth. And so it would just be the opposite value you got when approaching 0 from the right side. So as we plug in tinier and tinier negative values, the y value becomes a larger and larger negative value. And we also looked at y equals 1 over x squared. In this equation, the only real difference is that when you plug in negative numbers, you square them. And squaring a negative number, let's say plugging in negative 2 and squaring it, you multiply it by itself twice, and the two negatives cancel, and you just get a positive value. And so because of that, anytime you plug in these negative numbers here, they square and become positive, and so your y values in this case are always positive. And the other key difference is that it approaches infinity on either side faster than 1 over x. Since now, if you're plugging in, let's say x is 1 over 1 million. So you're dividing by a millionth squared, and 1 millionth squared would be 1 trillionth. And so 1 over a trillionth would be 1 trillion. So the numbers approach infinity much faster as you plug in tinier and tinier x values, or x values that are closer and closer to 0. But in general, it does look very similar. Notice it just is much steeper than the graph of 1 over x, but they have a very similar shape. And likewise, for both graphs, what you can notice is that as you plug in bigger and bigger x values, the y values start to approach 0. Since, let's say you plug in 1,000 and you square it, you get 1 over 1 million, which is a very tiny fraction or decimal. And the larger the value, the smaller the fraction. And this is true for y equals 1 over x as well. It's just it approaches 0 at a slower rate. Notice how for y value or x values, let's say around 4, in each of these, that the 1 over x squared graph is closer to this x-axis than the 1 over x graph. But they both do approach 0 as x gets larger or as x gets more and more negative. So what I want to show you in this video is that when you have y equals 1 over x to any odd power, that it's going to look very similar to this curve here, this graph of y equals 1 over x, since this is 1 over x to the first power, the first odd integer. And likewise, when you have y equals 1 over x to any even power, it's going to look very similar to the graph of y equals 1 over x squared, since x squared, this is the lowest even power. And the main reasoning for this is that when you plug in negative numbers when it's raised to an odd power, the overall y value will be negative. For instance, if you plug in negative 2 to the third power, when you multiply this out 3 times, two of them will pair up and become positive, but there's always going to be one left over that flips it back to a negative number. So in this case, you get negative 8. Whereas when you're raising x to some even power, let's say minus 2 to the fourth, then all of them will be able to pair up and the negatives will cancel out and you'll get a positive answer. So when x is raised to an odd power, the negative values that you plug in will give you negative y values as the output. But when you have x to an even power and you plug in negative values, they're all going to cancel each other out and you'll get a positive answer as the result. So when it's 1 over x to an even power, the negative values will be positive for their y values. And when it's 1 over x to an odd power, the negative input values will give you negative output values. And we can verify this by making a table, just like we did with these two basic parent functions here, but the process is a bit time consuming. So just to save time, we're going to look at this on a graphing calculator. But I do encourage you to convince yourself that these patterns are true when, let's say, you have 1 over x to the third power or 1 over x to the fourth power. And you would do that by making a table and just plugging in values and trying to graph it for yourself.